Hello and welcome to the world of NDE 4.0. Today is a great day because we have a great guest. And it's the first time I have the honor to actually have another YouTuber as a guest here on this channel. A YouTuber from the world of Industry 4.0. Kudzai Manditereza. Kudzai, he has, I think it's now about 6,000 subscribers on YouTube. And I think it's about 16,000 followers on LinkedIn, which is a pretty impressive number. And actually, if you look onto his YouTube channel, which I will leave a link right here, you can find out that, there is a lot of knowledge about IoT, about OPC UA. I myself, I learned a lot about OPC UA from his channel, so that's good job. He runs a podcast on Industry 4.0, and he has a company which offers education for Industry 4.0. So I think I have said enough. Stage is yours, Kudzai, and please perhaps use a few more words on introducing yourself.
Okay, thank you so much, Dr. Johannes, for welcoming me onto your platform. It's so great to be here today, sharing information about Industry 4.0. And I think you're doing a great job also on your channel. I've seen you actually grow from like 300 subscribers up until to over 1,000 now. So I think you're doing a great job. So it's great to be here, and I look forward to share this information that I've got here with your audience. Today, I'm going to be talking to you about the fundamentals of developing Industry 4.0 applications for manufacturing organizations. So this is a guide for industrial IoT or Industry 4.0 system architects, plant managers, digital transformation specialists, or anyone else who's interested in finding out the different pieces or how the different pieces of the puzzle from the operations technology and IT information technology come together for a common purpose, that is smart manufacturing. So I'm going to be focusing mainly on the reference architecture model for Industry 4.0, which was developed by the platform Industry 4.0 over there in Germany. So now, one of the biggest drivers of Industry 4.0 is the need for manufacturers to shift from mass production to mass customization of products, right? So this is driven by the fact that in this modern society, there's an increasing desire for people to actually customize their goods, customize their product. So what does that mean? What that means is that more and more people and businesses prefer customizing their orders when they're making purchases from manufacturers in order to suit their individual or organizational needs. So this could be things like your industrial equipment, it could be a furniture, it could be a car, it could be clothing, or whatever. So in fact, industry analysts are predicting that the next decade of innovation in manufacturing will be driven by the demand for mass customization. So to put it as simple as possible, manufacturers who are able to produce a product at lower prices and with customer-specific characteristics as quickly as possible will have the highest competitive advantage on the market in the coming decades. And the good news is that possibilities for capturing customer-specific requirements and producing customer-specific products have been opened by new technologies such as the Industrial Internet of Things, edge computing, artificial intelligence, additive manufacturing, and more, all collectively known as Industry 4.0 technologies. Now, here's the thing. Traditional mass production, otherwise known as Industry 3.0, sought to minimize production costs by using highly automated assembly lines designed for producing one kind of product with strictly defined characteristics and perhaps with a small number of variations of the product. Now, you see, in as much as that does reduce the cost of production significantly, it seriously restricts the flexibility of production, right? On the other hand, mass customization using Industry 4.0 technologies, as highlighted earlier, it allows the maximum flexibility during production at reasonable costs. So simply stated, traditional mass production or Industry 3.0 is focused mainly on production efficiency, whilst Industry 4.0 is focused mainly on customer satisfaction, right? So to help you implement a smart manufacturing strategy, today I intend to give you a detailed description of an architectural approach for the design of an Industry 4.0 manufacturing system by means of a reference architecture. And specifically, I'm going to discuss the reference architecture model for Industry 4.0, otherwise known as RAMI 4.0, which was, again, developed by a German initiative called Platform Industry 4.0. Right now, but first, we need to set the context, right? So we need to take a step back and look at the trail of how manufacturing systems have evolved over the past century or so, right? So initially, manufacturing systems consisted of production lines with machines that were dedicated to the performance of specific tasks so that only one type of product could be produced, right? And then next, there was the introduction of programmable machines. That was sometime around the mid of the 20th century, right? So with the introduction of the programmable machines on the factory floor, this allowed the production of a variety of different products, but still it offered no flexibility in how much of the same type of product the system could produce, right? So now today with Industry 4.0 technologies, the manufacturing systems are now able to self-adapt their hardware and software components to follow the ever-changing market requirements for both type and quantity of the products, right? So this reconfigurability of manufacturing systems is a typical feature of Industry 4.0, and it is the latest advancement in manufacturing systems. And it is what enables mass customization down to a production batch size of 1. So now the question is exactly how does Industry 4.0 enable things like mass customization in manufacturing and many other benefits like predictive maintenance and so forth. So here is how. So as you might be aware, if you are in the manufacturing space, there are different aspects to running a manufacturing business, right? There are top level strategic management processes, and there are planned for production processes. There is procurement and shipping and so on. And as is typical with traditional manufacturing, these aspects of manufacturing are not connected at all. They are totally isolated, right? Now, the fundamental idea of Industry 4.0 is that to achieve the much desired system reconfigurability, which results in mass customization, rapid product development, more efficient supply chains, and better use of production resources, these highly diverse aspects of manufacturing need to be integrated across the entire value chain into one common model, right? So to achieve that with Industry 4.0, these manufacturing enterprises, this aspect of manufacturing needs to be integrated into what are called groups. Like these are 4 aspects that Industry 4.0 identifies, right? The first aspect is vertical integration. So this is integration of all the systems that are used in a manufacturing business value chain, from strategic management at the top down to the plant floor vertically, right? So simply put, vertical integration within the factory describes the networking of the means of production. For example, it describes the networking of your automation devices or your services with high-level enterprise applications. So the second aspect of manufacturing that is identified with Industry 4.0 is the horizontal integration. So this is the integration of all the systems that are involved in your manufacturing supply chain, right? From procurement to shipping, and it extends well beyond the individual factories or manufacturing enterprises, right? And then next, there is the aspect of intelligent or smart production processes. So this is the integration of the various steps of processes that are involved in a manufacturing business life cycle, from the production design phase to the retirement of a product. And also, it is also involved the definition of the capabilities of the production processes. And then lastly, the fourth aspect to manufacturing that is identified by Industry 4.0, it's actually a totally new aspect to manufacturing systems. It is the establishment of intelligent or smart products, right, whose technical, commercial, and administrative data is kept consistent and made accessible within the entire value stream at all times, right? So intelligent products are products that are uniquely identifiable. They can be located at all times, and they are aware of their own current production status. And they also know their production and testing history, and they also know the requirements that are needed to achieve their targets. Now, having established these aspects, so the next step will be to unite them into a single model, because that's what Industry 4.0 is all about. Bring all these aspects of manufacturing and unite them into a single model. But that presents a challenge, right, due to the fact that these aspects are from different application domains that don't normally mix. For example, industrial automation and supply chain management are two separate domains that ordinarily wouldn't exchange information. So hence, it was necessary to establish what approaches and methods existed in each domain. And when that was done, it was clear that there was already a set of existing approaches or standards in each domain. For example, in the industrial automation domain, OPC-UA already existed as a standard of information exchange between automation services and top-level applications such as the ERP systems. Now, as you would imagine, in attempting to identify standards that could be used for cross-domain integration, there were highly divergent interests, right, from industries with totally different standards and techniques, right? For example, you've got the IEC, you've got the ISO, you've got the VDMA. These are all different industry bodies. So it makes it challenging to actually identify what standards to be used for each purpose. So in order to achieve a common understanding of what standards are necessary for Industry 4.0, it became necessary to sort of develop a uniform architecture model that can be used as a reference point to provide guidance and to identify, analyze, and resolve some common and important architectural concerns. So that ultimately it can be used as a template for anyone who wants to build Industry 4.0 applications. So this is what led the platform Industry 4.0 to come up with what is called the reference architectural model for Industry 4.0. Okay, so now we're going to look at the reference architecture model for Industry 4.0, which is called RAMI in short. So as I've already highlighted, the goal of RAMI was to come up with a framework that is representing a manageable architecture that can be used as a frame of reference for Industry 4.0 application development, and also to help identify and position where to put existing standards, and also to identify positions where there are gaps in standards. Right now, as much as it would be nice to build smart factories from the ground up, the reality on the ground is that most developments of Industry 4.0 will be done on top of existing legacy manufacturing systems because of their prevalence in the manufacturing space currently. A lot of companies or manufacturing facilities still use legacy technologies to produce their goods. So as you will see shortly, as part of this model, RAMI 4.0 itself expands on the hierarchy levels of the IEC 62264 standard, which is otherwise known as ISA 95, right, which is the standard with which the legacy manufacturing facilities are currently or they previously using to implement their systems. So perhaps that's a reason for us to pause for a moment here and take a quick look at the traditional implementation of manufacturing systems. So as you can see from this fairly common diagram, legacy manufacturing systems, they typically employ a pyramidal network and system architecture, right, which is based on ISA 95. So this is an international standard for developing an automated interface between enterprise and control systems, right? Now, these hierarchy levels represent the different functionalities within a factory or a manufacturing facility. Right, okay, so what RAMI does is that it takes all those crucial aspects that we've identified of Industry 4.0, your vertical integration, horizontal integration, smart products and the likes, and it actually tries to combine them into a three-dimensional model so that they can be classified and developed further, right? So that would help at least to pave the way for the breaking down of these complex interrelations that I've mentioned across different domains into something that is smaller and much simpler to manage. So now, but what exactly do we mean by the this 3D model? Because even myself, as I was trying to understand RAMI initially, when it was introduced to me a couple years back, was the idea of a 3D model really didn't make sense. So this is what I would like to try and break down for you to say, how exactly do we come up with this kind of a 3D model? So in simple terms here, we're saying that the RAMI model is a 3D layered architecture because in addition to the hierarchy levels that we just spoke about for ISA 95, the hierarchy levels that point where a certain component lives in the organizational hierarchy of a manufacturing facility, the components themselves have layers that need to be defined, right? For example, whilst a pump might live in the field devices level of the manufacturing hierarchy, we also need to define layers that exist within the pump itself, right? So this could be the physical properties of the pump, it could be the communication abilities of the pump, and it could be its ability to be integrated with other components. So this is what calls for the creation of a separate axis to capture these layers for each component, right? And similarly, each component in a manufacturing facility goes through a life cycle, right? From the time when it was just a simple idea to its creation, commissioning, usage, and up to the point where it gets decommissioned, right? And we also need to capture that life cycle and the value stream that it creates along the journey, right? So that's the reason we need another third axis, which is the life cycle and the value streams axis. So this is what eventually leads us to come up with this 3D model of RAMI, right? So as you can see, such a model should enable us to identify the existing standards for each layer on each axis, right? And it should be able to enable us to identify where there are gaps in standards, to close some loopholes and identify where the standards overlaps, and then we can actually come up with an agreement. So RAMI basically it's an abstract representation of this concept, but it is meant to actually act as a basis for further discussion. It doesn't impose or say specifically that this standard needs to be used for a communication layer of a component, or this standard needs to be used for such and such. It just gives you an abstract representation of an architecture to then carry the discussion forward. So these different organizations come together and then try to work together to identify what standard could be used where, and where there are overlaps, where standards could be used interchangeably. Right, now let us look at these 3 dimensions in a bit more detail, right? Now, starting with the hierarchy levels dimension, right? So this dimension essentially serves as the vertical integration within a factory, right? And what that means is that it describes how a factory asset can be assigned to an organizational hierarchy. So with RAMI 4.0, these are represented as levels of a manufacturing organizational hierarchy to which an asset could be assigned, by defining the roles and responsibility within a manufacturing facility. So you have got your field devices which are responsible for sensing and manipulating the production itself, right? So that's a role and responsibility. So you can identify what assets belong to that level. So now, however, RAMI doesn't define these levels from the ground up. Instead, it uses the ISA 95 hierarchy levels that are already being used for implementing most factories today. As I've already highlighted, that's the reality that is there. We need to work on top of something as opposed to try to define something from scratch, right? Now, but in order to extend the functionalities of the ISA 95 to reflect what has been made possible by Industry 4.0, they expanded this traditional hierarchy by including product right at the bottom, so as to capture the aspect of the smart product that we introduced earlier, to say this is a new thing. Smart product is a new thing because, as already suggested in Industry 4.0, the actual product that is being manufactured is intelligent, and it may contain some functionality during production, and therefore it needs to be seen as part of the solution, which can influence the production process itself, right? And then RAMI 4.0 further enhances the ISA 95 hierarchy levels by including the connected world at the top, right, to signify a link to the connected world outside the factory. So this link is made possible by, obviously, industrial Internet of Things, because now we are able to communicate information out of a factory. And this could be connecting different manufacturing facilities of the same organization. And it could also actually be extending beyond that enterprise to some external engineering firms and some customers or even suppliers, right? So now moving on to the layers dimension, right? Now, this dimension here represents the architecture of components within a manufacturing facility. So as I've already highlighted, that the component itself, right, we need to define the layers that exist within that component. So a component in this case could be anything that could be represented in the production process. So that could be a physical machine, it could be a software application, it could be a document, it could be a human being, whatever. So to get a clear view of the abilities of that component that is in question, RAMI decomposes the architecture of a component into layers, right? And these are 6 layers to be precise, which are, we've got the asset layer, and we've got the integration layer, the communication layer, information layer, the functional layer, and then at the top, we've got the business layer. Now, the asset layer at the bottom here, it represents the physical properties of the component. For example, this could be like some metal parts, or it could be a circuit diagram, it could be a barcode, QR code, or it could be like a document, a Word document, a physical paper, right? And then the next level is the integration layer, right? So the integration layer of a component provides information about that component in a form that can be digitally processed so that it can be integrated with other components in that manufacturing facility, right? And in Industry 4.0, this would typically be implemented as a sort of like a digital twin of the component, right? An example standard in this context is the asset administration shell. So I'll briefly go through the asset administration shell at the end of this presentation. Now, it is through this integration layer that components that are not capable of communicating for themselves can be involved in the information involved, right? For example, you could have some mechanical components that have got no electronics within them. They need to be included as well. So this is where the integration layer comes into play. And also you as a human being, you're not obviously capable of communicating electronically, obviously, and up until maybe Elon Musk perfects his Neuralink, we then will be able to communicate electronically. But right now, we only depend on HMIs, your human machine interfaces, to communicate, to input our information there. So even to exist as a digital twin as an employee, you've got to put your information into an HMI, right? So that's the integration layer. And then next, we've got the communication layer, which is responsible for providing a standardized form of communicating the digital information about that particular component, right? So it does that by using like a common data format and some predefined protocols. So this layer also provides services to the integration layer, right? So one common standard here used in this context is OPC-UA. So as you know, OPC-UA has got some services that it provides to the underlying information, which is your integration layer, right? And then next, we've got the an information layer, right? So this is the layer that is responsible for processing data about the component, right? And then it also persists that data into a well-defined information model to ensure that there's data integrity, and it also makes it available as useful information via a service interface. So in other words, what I'm saying is that this layer enforces what is called semantic interoperability, right, of a component, and thereby making its data representation and access Industry 4.0 compatible. So the idea with the information layer is to make your component, be it a robotic arm, a software application, the idea is to make it Industry 4.0 compatible by defining those information models that can be understood by every other component, right? So each component needs to have that layer as defined by RAMI 4.0. And then there's the functional layer, which includes the formal description of the functions or services that particular component provides in a smart manufacturing setup, right? So in addition to the functional layer, it also has some decision-making logic, right, that it executes, and it serves as a basis for your business processes. So if you've got business processes that need to be executed, these are handed over to the functional layer. This is what is responsible for executing those business processes, and it also serves as a basis for remote access and horizontal integration aspect of smart manufacturing. Because as we explained earlier, that with Industry 4.0, we've got that horizontal integration aspect, whereby we've got a supply chain or some component from a supply chain that wants to communicate with the component inside of a manufacturing facility. So the functional layer is what serves as that endpoint, as that remote access point that any component in the horizontal space can use to control or collect information from that manufacturing facility. right? Now, in short, what we're saying is that the functional layer provides the Industry 4.0 compatibility as far as the functional access of the component is concerned. And an example of functions that could exist in this space are your ERP functions, right, in a manufacturing context. And then lastly, we've got the business layer, which also needs to be defined for each component. And what we're saying here is that what manufacturing business processes is your component linked to, and are there any legal or regulatory conditions that the component needs to operate under as far as those businesses processes are concerned? So that is what this axis of layer is all about. It's about it gives a perspective on the information technology aspect of smart manufacturing systems, right? Okay, moving on to the life cycle and value streams axis. Now, this dimension is based on another standard, which is the IEC 62890 standard, which is responsible for establishing the basic principles for life cycle management of systems and components that are used in industrial systems. So in these dimensions, there are two elements that are being addressed here. So we've got the type and we've also got the instance. So the type part describes a component in its basic idea, right? Before it is even before if it isn't it's realized, before it is made real. So the type part is when you are conceptualizing the component before you even manufacture it, right? So even the conceptualization, it extends to the development phase and maintenance to say you can simulate to see that when you are now using this product, how is it going to behave, or how much value is it going to provide down the line. So the type part consists of the development and the maintenance usage aspect of it. And then on the other hand, we've also got the instance part of the life cycle. So the instance part, like I've just highlighted, it describes the concrete assets after it's been manufactured, right? And based on the idea of the type stage. So all the information from the type stage obviously carries over to the instance when the actual component is now a concrete reality, something that is physical, something that can be touched, or something that is now in reality if it's a software system. So the instance, again, it ranges from production usage to maintenance of the of that particular component. So here is a simple diagram that shows the types and instances in a life cycle, right? So you could see there we've got the types and instances of a supplier part, or for example, or machine, or even the factory itself. Because remember, the factory itself is considered to be an Industry 4.0 component. It's an entity on its own that it needs to be that can actually stand on its own and be identified as an Industry 4.0 component. So it is also subjected to this life cycle and value streams approach to smart manufacturing as defined by RAMI 4.0. Right, and then now, before I end this session, I'm just going to briefly introduce the concept of the asset administration shell, right? So basically, the asset administration shell is a way of trying to come up with a unified model for describing Industry 4.0 components. Because in the previous sections of this presentation, I've been describing the layers of the components and things like that. But we've got that integration layer where we need to describe a component to say if it's a robotic arm, or it's a sensor, or it's a factory. Can we come up with a unified model of describing these components? So that's what the asset administration shell is all about. So the asset administration shell does that by providing a visual representation of the real physical asset and the data for the current status information of that asset, and also the data which was generating during the life cycle of that asset, all in a consistent format. So we've got a component that has been conceptualized. You need to capture that information and present it, and that information needs to be available to other aspects of manufacturing for the entire life cycle of that asset. So conceptualization, manufacturing, production, even when it goes into a production process, we also need to be obtaining the current status information of that asset. So the asset administration shell is a way of trying to come up with a unified model of describing these Industry 4.0 components, right? So now, in conclusion, how does this information actually help, like RAMI 4.0? Because you could be asking a question, okay, we understand this, so but how exactly does it help someone build or architect a system? So what it does, that it helps in the sense that it gives all stakeholders a unique perspective, right? Whether you're in IT, you're a plant manager, or you're an original equipment manufacturer, you are able to actually look at it from your own perspective, right? So let's say, for example, you are an OEM manufacturer. You could look at the layers in the layers dimension and ask yourself, if I want my equipment to be Industry 4.0 compliant, what standards should I use at each layer of my component, right? And because RAMI 4.0 exists, it will guide you on what standards are available to use for all the different layers of your component that you are manufacturing as an OEM. So that even as an IT person who wants to integrate operations technology, it also provides you that view to say there's an information model that is that describes all the information about a particular component, and you know exactly how to consume that information and how to present it in an analytic apps, or if you are using a machine learning algorithm, you also know what sort of information, what structure of information to expect. So it gives everyone a unique perspective, all in a unified model that is common to the smart manufacturing purpose as an end goal. So that brings us to the end of this presentation. So that's brief information about myself, which Johannes has already told you about at the beginning of this session. So thank you so much for your time, and it was really, I really enjoyed imparting this information to you. Over to you.
Kudzai, thanks a lot, and thanks for introducing those great concepts to, the listeners to, or the viewers to that video. I think both those concepts are really important for Industry 4.0, to understanding for Industry 4.0. It might be that some of you might think that RAMI sounds a little bit difficult, but actually, if you look into it, it's not that difficult. It's really for seeing, okay, do you already have all the standards you need for all the different connections you need to establish to get into a smart factory, to get into highly customized production, and so on. And asset administration shell, that's for me, that's a really important step, because that is the first step to actually build a framework for digital twins. And once you understood that, because currently every digital twin you see out there, all those fancy 3D visualization digital twins, they are all programmed for a specific application. It's not a framework you can use and just modify so that you get a result. No, it's all done from ground all the time again. But the asset administration shell will be a baseline which you can use and just build on top of it. It will reduce the development time drastically, and so it will really change the whole concept of digital twins, I guess. Now, it's time for you to ask us questions. And because Kudzai and myself, we will do another video where we will actually answer all your questions. And I will also try actually to get some of the people perhaps from the platform Industry 4.0 also as a guest for joining our conversation, so that we have even a better view on all the things we discussed today and all the questions you will be asking us. I think this was an excellent presentation. I think this excellently fits to the world of NDE 4.0. Perhaps for some NDE people it's a little bit far out, but I guess in 2 or 3 years you will get into that those are concepts you really need to get into. So it's good to hear it here in the beginning and then start working your knowledge to a point that you understand it, and once you need it, that you can use it. So, that's it for today. Thank you for watching. See you soon. Thank you, and bye.
Bye.